Hello everyone and welcome to A+ Physics. I'm Dan Fullerton, and in this video we're going to take a look at the 2017 AP Physics 2 free response problems. So let's dive right in, looking at number 1, a fluids problem. We have a couple students who are watching water flow from left to right through the section of pipe that's shown in the diagram. Not quite sure how they're watching it, but hey, who knows? Now, that pipe decreases in diameter and increases in elevation. The pipe ends on the right, the water exits vertically, and at point A we know some stuff about the water. Now, it then says the students disagree about the water pressure and speed at point B and make a couple claims. Well, Y claims the pressure at point B is greater than that at point A because the water is moving faster at point B. What aspects of that claim are correct? Well, from that claim, the only thing that I see correct is that the velocity of the water at point B is greater than the velocity of the water at point A, and we know that due to the continuity equation. The area times the velocity at any given point in that closed pipe has to be the same. So since it is thinner, has a smaller cross-sectional area at B, it must be going faster at B. Now for part 2, what parts of Y's claim are incorrect and support your answer using appropriate physics principles? Well, I think Y is incorrect in stating that the pressure at B is greater than the pressure at A. The water at B is moving faster and is at a higher point than at A, so the kinetic energy and gravitational potential energy aspects are both greater than at A, which means the pressure at A must be higher to keep both sides of Bernoulli's equation equal. And what we're talking about when we look at this in terms of Bernoulli's principle, we can say that the pressure at A plus 1/2 rho VA squared, the kinetic energy equivalent at A, plus the gravitational potential energy part, rho GYA, must be equal to the pressure at B plus the kinetic energy component, 1/2 rho VB squared, plus the gravitational potential energy component at B. Now, if we call A point, our lowest point, if we call that a height of 0, then we could say that YB equals 5. We can rearrange this a little bit to write that, well, if we call YA 0, our 0 point, that whole term becomes 0. We can then rearrange this to find that the pressure at B minus the pressure at A must be equal to 1/2 rho VA squared minus 1/2 rho VB squared minus rho G times YB, which is 5 meters above where A was. And if we just analyze this a little bit, if VB is greater than VA, this must be negative. And we can see this is negative. Density and acceleration due to gravity here on Earth, 10 meters per second squared, is both positive. So this whole term becomes negative. PB minus PA must be less than 0. Therefore, as we look at this, we could say that the pressure at A must be greater than pressure at B, which is a way to mathematically prove what we're saying when we say that that part of student Y's claim is incorrect. So I think that covers us pretty well for part A. When we move on to the next part, though, it now says indicate any aspects of students Z's claim that are correct, where Z claims the speed of water is less at point B than at point A because of conservation of energy, and some of the water's kinetic energy has been converted to potential energy because of the Earth-water system. What part of that claim is correct? Well, you might have to stretch to find something correct here. Nice use of grammar and punctuation, perhaps? Or you could say that the law of conservation of energy certainly applies, but it doesn't apply in the way that Z is stating that it is. So not much is correct about student Z's claim. What parts of that claim are incorrect and use appropriate physics principles? Well, I would say that Z is incorrect in stating that the speed is less at B than A, as we already showed by the continuity equation. And if we wanted to, just to make sure that anybody grading this, the readers, are very clear on what we're talking about, the cross-sectional area at A times the velocity at point A must be equal to the cross-sectional area at B times the velocity at B. Or rearranging that, Since we know that the cross-sectional area at B is less than the cross-sectional area at A, we could state that the velocity of A is less than the velocity at B. So that would be one way you could talk about that being incorrect. Let's move on. Next, we're asked to take a look at point B and find the speed of the water and the pressure of the pipe. Well, let's start by giving ourselves a little more room here. And as we think about this, how do we find the speed of the water? Well, we've actually done this calculation, everything but the actual numerical replacements, when we talked about the continuity equation. The cross-sectional area at A times the velocity at A must be equal to the cross-sectional area at B times the velocity at B. Therefore, the velocity of the water at B must be the area at A over the area at B times the velocity of A. And if these are circular pipes, that cross-sectional area is pi r squared. So that's going to be pi times 2.5 squared over pi times 1.5 squared. Our units are just going to cancel out anyhow, so we'll not worry about them for the time being, times the velocity at A, which we know is 0.5 meters per second. Little bit of calculator work, and that comes out to be right around 1.39 meters per second. Now, to find the pressure in the pipe, we're going to go back to Bernoulli's equation, something we've already brought up briefly. So, as we go into Bernoulli's equation, pressure at A plus the kinetic energy component, 1/2 rho VA squared, plus the gravitational potential energy component, rho GYA, must equal the pressure at B plus 1/2 rho VB squared plus rho GYB. And with just a little bit of rearrangement, since we're looking for the pressure in the pipe at point B, let's solve this for the pressure at B. And I come up with the pressure at B is equal to 1/2. And then if we combine our kinetic energy terms, that's 1/2 rho VA squared minus VB squared. We also have the gravitational potential energy piece, and we can combine these, YG rho A minus YB, YA minus YB. Then all we have to do is add the pressure at A. And now we can substitute in our values, which implies then that the pressure at B is equal to 1/2 density of water, 1,000, VA 0.5 squared minus, we just figured out at B it was 1.39 meters per second squared, plus rho 1,000 times G 10, YA minus YB, that's going to be 0 minus 5, or just -5, plus the pressure at A, 2 times 10 to the 5th pascals. Which implies then, plugging that all into my calculator, the pressure at B comes out to be right around 1.49 times 10 to the 5th, or 149,000 pascals. All right, let's move on and take a look at part C. In part C, we now close the valve to the left of point A. The section of pipe shown still full of water, but the water is no longer flowing. Calculate the absolute pressure at point A. So we're including the effect of the atmosphere. Well, the absolute pressure is just P0 plus rho GH, where there's our atmospheric pressure, which we can estimate is about 100,000 pascals, plus rho GH. 1,000, our density, kilograms per meter cubed, times G, 10 meters per second squared, times our height, 6 meters. Put all that together, 160,000 pascals. And for part C2, we have an air bubble that forms at point A. Draw a free body diagram for the air bubble. Well, that should be pretty straightforward. Air bubble, nice little dot. Of course, we have gravity pulling it down, mg, and we have a buoyant force up. And I might even write out buoyant so that we're certain the readers know what we're talking about, and make sure the buoyant force is a little longer than the weight. I think that covers us for number 1. Let's move on to our electrical question number 2. All right, group of students given several long, thick, cylindrical conducting rods of some unknown material, along with a little bit of electrical lab equipment, and were asked to find its resistivity. Describe a procedure we could use. Now, what I would probably do here is hook that up into a series circuit, measure the current through that rod and the voltage across it at various voltages. So we have various currents to go with various voltages. Plot those, and we should be able to use that in order to get the resistance of that material, of that object. Once we know the resistance of the object, if we find its cross-sectional area and its length, we should be able to back out the resistivity. So first, I'd probably draw a circuit. We'll start off with our variable power supply, run that to our ammeter, and I'm going to draw our unknown material as a resistor, but it's probably worth saying that this is our rod, just so the readers know that we're calling that a resistor. And across that, measured in parallel, we put our voltmeter. So we'll get the voltage across the rod and the current through the rod. Then our procedure would say something like, I'm going to set up a series circuit with the power supply ammeter in one of the rods, place the voltmeter in parallel with the rod, which we've already done by our diagram, adjust the power supply to provide various voltages, each time recording the current through the circuit from the ammeter. If we then plot voltage on the y-axis and current on the x, hopefully we get something fairly linear. The slope of that should give us our resistance, R equals V over I. It's kind of a tough color to read there. Slope equals R. And if that's our R, remember R equals rho L over A, so resistivity must be RA over L. So our resistivity is going to be our slope times the cross-sectional area of our cylindrical wire, pi r squared, if we measure the radius of it, divided by its length. So make sure when you talk about doing the graph and stuff, you mention the best fit line, determining the slope of the line, and having that fit the equation y equals mx plus b, where x is your current, y is your voltage, and your slope, m, becomes your resistance, or rho L over A. And yeah, I think that'll get you through that one. Draw your procedure there. Now, it's going to complicate things a little bit. Now they're giving the students a long, thick, cylindrical conducting rod of the same unknown material. Oh, now we're given a rectangular rod of the material. The dimensions aren't known, and students are asked to experimentally determine the resistance of the rod. They obtain the data in that table below for the potential difference, the voltage across the rod, and the current in it. So let's give ourselves a little more room here. And it looks like what we're going to do is plot the data. All should be pretty good at plotting data by now, I would think. So we've got current on our x, we've got potential difference, delta V in volts on the y, and scales 0.01, 0.02, 3, 4, 5, 6, 7, 8. So this will go up to about 0.08, 1, 2, 3, 0.04, 0. And for voltage, 1, 2, 3, 4, 5, 6. Don't think we have to go above 6 volts, but we'll put another tick mark or 2 there. Now, plot points. Should certainly be able to plot points by now. And when you do that, we'll get something that I believe 6 was at about 0.078. So we're over here. Down at the low end, we had 1.5 and 0.018. So somewhere in here, and a number of points in between. Next, go draw a best fit line. Does not have to go through all the points, but matches. So you have roughly the same amount of space above and below your data points. Use the best fit line to determine the resistance of the rod, showing your calculations. Well, slope is going to be rise over run. What I like to do here is don't use data points, but circle the actual points that you're going to use. So when I did mine, I had a point over here and a point over here, which corresponded to 6 volts minus 3 volts over 0.08 amps minus 0.04 amps. A little bit of calculator work tells me that that comes out to be about 75 ohms. So that's how you could use the graph to find the resistance of the rod. Very similar to what we did in the previous part, almost a little simpler even. All right, taking that to the next step. We complete our calculations and we begin to think about where we could get some uncertainties in our results. And the first thing it says is the students realized that they didn't take into account any internal resistance for the battery, power supply, whatever it happens to be. How would this affect the value of the resistance, and explain your reasoning? And this one's pretty simple. Because we have the voltmeter wired up to read the voltage only across the rod itself, across our resistor, not across the whole circuit, the internal resistance of that battery or power supply really doesn't make any difference. We've got our more accurate measurement, so the battery's internal resistance shouldn't have any effect on our readings. C2, however, says the students realized they did not take into account a possible change in the temperature of the rods. Should we be concerned, and why or why not? All right, and this can be a little bit of a tricky question. Technically, that is a legitimate concern, as shifts in temperature do have a small effect on resistance. Typically, as things get warmer, their resistivity goes up. But it tends to be a secondary or smaller effect, so practically, unless things are getting really hot, probably doesn't have a whole lot of effect on the circuit. But I would answer that as simply as possible and say it's a legitimate concern. Shifts in temperature do have a small effect on resistivity. Make it nice and simple, and we'll go right on from there. Pardon me. On to our optics question. We're asked to determine the focal length of a convex lens. So we have a light box, we've got a plate on the hidden side of the box with a little symbol in there, a little screen, a lens, and we set this all up on a ruler so it's pretty easy to measure what's going on. Now, first thing it says is on the figure below, sketch how the image on the screen appears to the students. And initially we can see that our object looks like this. So on the screen, what is that going to look like? Well, on the screen, remember, everything is reversed. So where it's going up, we're going to have it pointing down. We had the dot on the right over here, so on the screen, we would see that over on the left. Nice, simple way to answer A. Of course, we're going to get a little bit more involved here. For the next part, B, find the focal length of the lens. And for that, we can use the lensmaker equation. The if I do, I die. 1 over the focal length equals 1 over the object distance plus 1 over the image distance. In this case, our object distance is 20 centimeters, and our image distance is 30 centimeters. So 1 over 20 plus 1 over 30, little calculator work, and that's about 0.08 with a 3 repeating, and the units would be 1 over centimeters. So if 1 over the focal length is that, then the focal length must be 1 over that, which is 1 over 0.083 repeating 1 over centimeters, or a nice happy 12 centimeters. In part 2, find the magnitude of the magnification of the image. So since it's asking for magnitude, we don't have to worry about the negative sign, but our magnification is minus di over do. Again, we don't really care about the negative sign since it's asking for magnitude, so let's put magnitude equals that, which is going to be 30 centimeters over 20 centimeters, or about a magnification of 1.5 x. So a couple more straightforward there. I'm sure we're going to get a little bit more detailed here in a second. All right, next up, it looks like we're going to do a little bit of ray tracing. A side view, the arrow represents the bright object created by a plate. Draw a ray diagram that's consistent with your calculations and show at least 2 rays, as well as the location and orientation of the image. So you guys have access to the prettier principal axis. So I'm just going to sketch this in generally what I have here, but we'll say this is 10, 20, 30, and about the same over here. 10, 20, 30, 40. And we've got our object over here at 20. All right, draw a ray diagram consistent with your calculations in parts B1 and B2. Well, one of the first things we need to note is if we're doing some ray tracing, the ray from the top of our object that goes through the center of our lens just goes straight through. No bending to be worried about. The second one that we're going to deal with goes parallel to the principal axis until it hits the lens. Oops. And then it is going to get refracted through the focal point, through the focal length of our lens, or through that 12 centimeters. And if it does that, we know that it should meet over here. So I'm going to cheat a little bit as I draw it, not having quite the pretty screen you have. That should be crossing right there at 12. But these points meet right over here, which means our object would look like that. And that crossing point must be at 12 centimeters, which is our focal length. So there's 20 centimeters, there's 30 centimeters. I think it says that's negative 30. And we're going to explain how our diagram is consistent with the calculated focal length and magnification. So you might state, probably in paragraph form, the ray from the object parallel to the principal axis travels through the lens and is refracted through the focal point on the image side of the lens at negative 12 centimeters. The ray that goes through the center of the lens at the principal axis travels through in a straight line. There it goes. And where these rays converge at the image distance of 30 centimeters, or negative 30 centimeters on the axis, as anticipated, provides an inverted image which is 1.5 times larger than the object. Everything we expected from our calculations. All right, now we're going to get out into the weeds a little bit. The entire apparatus is now submerged in water, whose index of refraction is greater than that of air but less than that of the lens. So if we assume the lens is glass, an index of refraction somewhere in the 1.5, 1.6 range, water typically about 1.33, and air 1. So we're going to have less refraction at each boundary when we have water as the ambient compared to air. So knowing that, the first thing it asks us is to draw what happens as we look at the two areas of refraction on the lens in air and lens in water. I'm just going to sketch this very roughly. The one in air, we have our ray coming in horizontally. When it does that, we're going to draw a normal to the surface, and it's going to get refracted toward the normal. Probably not a whole lot here. The next interface, we again have another normal. It's now going to get refracted away from the normal. So probably look something like, oops, that wasn't the color I was after. Let's try that again. So probably looks something like that, where we have air on the outside. Do the same thing where we have water on the outside. We'll start off with our ray coming in. Draw the normal line again. But now we're going to have a bit less refraction. And I probably should have exaggerated it a little bit more on the left to make this a little easier to see. But now we need to have less refraction than we had on the first one. And again, same thing over here. Draw our normal line. Again, less refraction than we had on the one in air. So each time it's refracting, it's bending down further, but it's certainly bending down more over here in air compared to over here in water. And in all honesty, if I had this to do it again, I would probably really exaggerate that, so it's very obvious to see what's happening in air compared to water. And describe how the focal length of the lens and position and size of the image formed by the lens when it's in the water compared to when it's in the air. Explain how the rays drawn in the figures in part D1 support your answer. So it's asking us to put a lot of this together, but I think just as we walk through a normal explanation, we'll hit most of these points. I'd say something like, when the lens is in the water, it has a longer focal length since the difference in index of refraction from the ambient to the lens is less in a water ambient compared to an air ambient. The water 1.33 to the lens about 1.5 compared to the air 1 to 1.5. So less bending of rays when the lens is in water compared to air. Because of this longer focal length, the image will form at a greater distance from the lens. With a larger image distance and the same object distance, the magnification of the system will be increased. Therefore, the size of the image is greater in water than in air. Hopefully that would cover you. I think you at least get pretty close there in most of the points. All right, let's move on to our electrostatics question. We now have 4 objects with charges shown held in place at the corners of a square. Point P is at the center of the square, a distance d from each of the objects. And what we're going to do first is draw an arrow showing the net electric force exerted on the object with the charge plus Q, the one in the upper right of that diagram. So we've got plus 2Q, plus Q, plus 2Q down here, and over here minus 2Q. And we're really worried about what's happening right there, so we're drawing that over here. And first thing I'd note, as far as electric field components, this minus 2Q is a lot further away than the 2Q's over here. And these two are going to cancel each other out as far as how they're pushing toward each other. So we're going to see, I would expect, a symmetry along that axis. So pretty obvious to me that 45 degrees we could draw the electric force in that direction, and that should cover us for 4A. Now for 4B, it wants us to calculate the magnitude of the electric field at point P over there in the middle due to all 4 objects, and then on the dot below draw an arrow to indicate the direction of the net field. Well, let's start by calculating the magnitude of the electric field here. We'll get rid of this for now. And the plus 2Q charges cancel across from P, of course. So that's going to leave us with these 2 charges, the plus Q and the minus 2Q to deal with. So let's start off with the minus 2Q calculation. The electric field is K times the charge over R squared, which in our case is going to be K times negative 2Q. We're really going to ignore that negative and use common sense to figure out the direction. R, that distance it tells us is d, so that's over d squared, so this becomes 2kq over d squared. Again, just worried about the magnitude for now, because we can obviously see that if this is a positive test charge, it's going to have a field in that direction, toward the negative. Now if we do this for the positive q, E equals kq over r squared, that's k times plus q, and the distance to point P again is, oops, not r squared, but d squared, or kq over d squared, and also, since it's repelling a positive test charge, in the same direction. So these electric fields, due to each of these charges, are going to add. So the magnitude of the total electric field is going to be 3kq over d squared. And the direction, let's draw it down and to the left. And for part 2, find the electric potential at point P due to all 4 objects. Well, that tends to be a whole lot easier since potential is a scalar. Electric potential is the sum of our kq over r's. K is a constant, so let's make that k times the sum of q over r, which is going to be k times, and then we just add these up for our 4 charges. We've got 2q over d. We've got plus q over d. We've got another plus 2q over d, and then we have to subtract 2q over d. So obviously those two are going to add up to be 0, so we end up with 3kq over d for our potential. So I think we've covered part B pretty well here too. Let's move on to C. All right. In a coherent paragraph-length response, describe the meaning of electric potential energy and explain qualitatively how electric potential energy can be related to work. All right, already this is starting to get to be a lot of writing and a pretty deep question. Understanding electric potential energy work, one of the harder concepts in electricity. So probably take your time here and understand your fingers might be a little sore by the time you're done writing your answers to these. Explain qualitatively how the electric potential energy, we'll worry about that part next. First off, paragraph length response. Electric potential energy describes the energy stored by the given configuration of charges. Specifically, that electric potential energy tells you how much energy it would take to assemble those charges and move them into the given configuration, assuming they all started theoretically an infinite distance from each other. So how much energy is it going to take to pull these charges from a far, far, far away and get them in that configuration? That energy is equal to the amount of work that would have to be done by some external force to move those charges from infinity to the given charge configuration. So that's a conservation of energy sort of a question there. Now things get a little tricky. Explain qualitatively how the potential energy of the four-object system would change if the plus q and plus 2q objects on the right side of the square now switch positions. All right, so the two on the right switch. The plus 2q in the bottom right comes to the upper right, and the plus q in the upper right goes to the bottom right. That's a pretty strange question. I'd say if the two charges on the right side were switched, you'd have to do work to move that plus 2q charge as you're getting it closer to that higher magnitude plus 2q charge in the upper left. So that's going to result in an increase in electric potential energy, while moving the plus q charge from the upper right to the lower right would result in work being done, decreasing the electric potential energy of the configuration. Because more work is involved with moving that plus 2q charge up compared to the plus q charge down, because that's twice as much charge on the plus 2q, it's heading toward that plus 2q, the net result is an increase in electric potential energy, as net work is done on the system to get it into that new configuration. So that's a pretty challenging sort of question there, and one that's probably good to be the last question on the exam, because you can keep writing and going into a lot more depth if you have the time, but if you don't have the time, get down what you can in this timed exam. So hopefully that gives you a pretty good feel for the free response questions from the 2017 AP Physics 2 exam. If you're looking for more help, need more information, check out aplusphysics.com. Thank you so much, everyone, for your time and attention, and make it a great day.